Unless you've been living under a rock, this shape probably seems pretty familiar to you, even if you can't quite put your finger on it. That's because it's from the game called Conway's Game of Life, and more specifically is referred to as a glider, because it glides in the direction that it's facing, as seen here. Now you might wonder, what's Conway's Game of Life? Conway's Game of Life, also known simply as Life, is a cellular automaton devised by the British mathematician John Horton Conway in 1970. It is a zero-player game, meaning that its evolution is determined by its initial state, requiring no further input. The rules to this game are that any live cell with fewer than 2 live neighbors dies, as if by underpopulation, that any live cell with 2 or 3 live neighbors lives on to the next generation, that any live cell with more than 3 live neighbors dies, as if by overpopulation, and finally that any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. Now, something that you might wonder about, or might have even done before if you've either messed around or even coded one of these, is try to expand the map size, which we'll do right now. So as you can see, we've expanded the map size to a 400 by 400 map. Let's put down some pixels, and let's play. And as you can see here, it's running at an astounding tab lagging frames per second. Alright, so let's pull out this second version of it, which is running using the exact same algorithm and on the exact same machine and browser as you can quite clearly see here. Let's run the game, and let's resize it to 2 to the power of 10 by 2 to the power of 10, which is even larger, at an astounding size of 1024 by 1024. Now let's resize the cursor to 100 by 100, place down a few of these, and run, and as you can see, it's running quite a lot faster than our other version. Now you might wonder, why?
Well, it works by using something called parallelization, where things are done in parallel. Now, how does that work? Well, each cell is its own individual unit, unaffected by whether the cell next to it dies or lives, at least for the tick that it's in. Now, this means that we can parallelize it pretty easily by assigning each cell to a different CPU core or thread. Even better way is to use the GPU. Now you may wonder, wait, on the GPU, but that's for graphics. The CPU is the chip that's used for actual calculations, while the GPU is used for stuff like, for instance, raycasting or Bitcoin mining. Well, CPUs and GPUs might not be as different as you think. GPUs are basically just more multi-threaded and more multi-core versions of CPUs. And you might be wondering by how much. Well, while your CPU might have 2 cores, or maybe even 8 or 16, GPUs can have hundreds or thousands of cores, which provides a pretty significant advantage in a ton of cases, including ours. To show you the scale of this drastic increase in the amount of calculations we can do, we'll be using the Core i9 12900K and also the RTX 3080 Ti as our reference points and comparing them against one another in terms of flops, or floating point computations. More specifically, the number of floating point computations that they can do per second in order to evaluate their speed, and because floating point operations are very, very important. Now, if we look at the Core i9 12900K, we can see that they can produce 166 gigaflops. Well, pretty nice. But once we get to the GPU, we can see that they produce a whopping 34.1 teraflops. just to get a sense of scale, that's roughly 205 times more processing power, which means that the GPU, in terms of pure computational speed, just outright wins. But then your question might be, why aren't we using GPUs for everything? Well, there's a reason for that. CPUs are the way they are for a reason, after all, and that reason is single core performance. Now, something you may have seen is that we're using JavaScript. Quite notably, not a language that's typically ran on the GPU. For the GPU ran language, we use GLSL shader language. Now, this is because the CPU is actually managing the GPU. This is because having a single core is a lot easier to manage and is basically necessary to manage multiple cores at that magnitude. With even CPUs doing the same thing, having a single core dispatch commands to the other cores. Oftentimes the processes ran on the CPU are ones that are inherently unparallelizable, or at least not to the scale that GPU cores provide and expect. In that case, of course, multi-core CPUs with multiple threads and even other types of computers like quantum computers can really help out. Oftentimes, these tasks are sequential in nature, relying on the output of the previous task in order to execute, thus making them impossible to properly parallelize on a GPU. Or maybe they are possible to parallelize, but aren't worth it in terms of computation due to the amount of time it takes the CPU and GPU to communicate, which is one of the biggest issues when programming things that deal with graphics. Not to mention the fact that optimization like this is oftentimes unnecessary and considered over-optimization due to the lack of need, which is due to how it can make the code harder to read, especially for beginners, and due to the current processing power of CPUs, which makes these optimizations unnecessary since the algorithms employed are quote-unquote fast enough. That isn't even mentioning cases where hardware acceleration is limited or not employed at all, meaning that CPU algorithms would indeed be the only effective option that could be used.
Now, in order to gain a deeper understanding of the code, what we'll do is take an actual deeper dive into the actual code. So, as you can see here, we create graphics, which is basically a canvas using the p5.js library, which is our rendering library, which will act as the front and back buffers of our simulation. Basically, where the front buffer is displayed and the back buffer is written to by the GPU, like what normal graphics do. And we compile the shader for each one since they're separate canvases. And for anyone that works with GPUs, graphics, OpenGL, that sort of stuff, I'm not using an FBO because I'm lazy. So yeah, and here we got the steps function, where each step we execute the shader. Well, we set the shader, we initialize it, we set the uniforms for it, and by initializing a shader, you're making it so that when something is rendered, OpenGL slash WebGL will apply that effect, that shader, to whatever you're rendering. Here's the shader code. We got the vertex shader. This vertex shader in specific simply just spreads the whole entire render over the screen, making it so that we render to the whole thing.
And this is the fragment shader, which is ran for each pixel, with each pixel corresponding to a cell.
And since each cell is a pixel, we need to get the pixels next to it, which means that since we're not using WebGL2 and thus don't have access to texel fetch, that we'll have to access it using the floating point coordinates, which are coordinates for each axis ranging from 0 to 1. And we take the inverse of each axis for screen size and we put that into another vector, which is the pixel size. Using the pixel size, We can get the coordinates of the cells next to our current cell and thus get their color. And we got a live cell color, dead cell color, and screen size. And we got the is alive and a counter to count the number of neighbors a cell has. And then to the back buffer, we render whether it's alive or not to the back buffer. And of course, the counting and whatnot is counting the cells next to the current cell on the front buffer. And that's how we calculate the whole thing. Pretty simple.
Anyways, as you may or may not have noticed, this is a pretty new channel with only one full-length video and one short otherwise posted, at least at the time of recording this audio recording. So, please, like, share, subscribe, because it really helps out. And I hope to be able to bring a lot more of these sorts of technical explanations to hopefully a lot more people.